A polynomial in one variable x of degree n is an expression of the form p of x equals an x raised to n plus an minus 1 x raised to n minus 1 plus etc. a1x plus a0, where a0, a1, a2, etc. an are constants and an not equal to 0. If the degree is 2, then it is a quadratic polynomial. A quadratic polynomial is an expression of the form p of x equals ax square plus bx plus c, where a not equal to 0, a, b and c are real numbers. For example, 2x square plus 3x plus 1, 2 minus x square and root 5 into x square minus 2 by 3 into x are quadratic polynomials. Now, if a quadratic polynomial is equated to 0, then it is p of x equal to 0, which means ax square plus bx plus c equal to 0. This is known as a quadratic equation. Quadratic equations arise in several situations in the world around us and in different fields of mathematics. Let's see an example. Consider this swimming pool. It is given that the area is 8 square meters and the length of the pool is 1 meter more than twice its breadth. Now we need to generate a quadratic equation with this information. Let the breadth be x meters. Then the length of the pool will be 2x plus 1 meters. So the area will be the length into breadth, that is 2x plus 1 into x, which is 8. Multiplying and rearranging, we get 2x square plus x minus 8 equal to 0, which is the form of ax square plus bx plus c equal to 0. That is a quadratic equation. So, a quadratic equation in the variable x is an equation of the form ax square plus bx plus c equal to 0, where a not equal to 0, a, b and c are real numbers. For example, 2x square plus 3x plus 1 equal to 0, 2 minus x square equal to 0 and root 5 into x square minus 2 by 3 into x equal to 0. Also, please note that the expression ax square plus bx plus c equal to 0 is the standard form of a quadratic equation. Now, let's work out a few problems. A pole must be erected at a point on the boundary of a circular park of diameter 12 meters in such a way that the differences of its distances from two diametrically opposite fixed gates A and B on the boundary is 8 meters. Generate a quadratic equation to get the distances from the two gates. To understand this better, let's draw the circle of the park, marking point P on its boundary indicating the position of the pole. Now randomly mark the diametrically opposite gates as points A and B and join them to get the diameter AB, which is 12 meters. Now join PA and BA, which will be the poles distances from the two gates. As we need to get these distances, let's consider one of them. Let it be BP as x meters. It is given that the differences of its distances from the two diametrically opposite fixed gates A and B on the boundary is 8 meters. So according to this information, we can write BP minus AP equals 8 meters. Then AP will be x minus 8. Since the angle in a semicircle is a right angle, angle APB is 90 degree. So triangle APB is a right angle triangle. By Pythagoras theorem, AB square equals AP square plus BP square. So 12 square equals x minus 8 whole square plus x square. Expanding x minus 8 whole square, we get 144 equal to x square minus 16x plus 64 plus x square. On further simplification, we get 2x square minus 16x minus 80 equal to 0. As all of the coefficients are divisible by 2, let's simplify by dividing throughout by 2. Then we will get x square minus 8x minus 40 equal to 0, which is a quadratic equation of the form ax square plus bx plus c equal to 0. Now let's check whether the following are quadratic equations. That is, we need to check if we can reduce these equations in the standard form of quadratic equation ax square plus bx plus c equal to 0. The first equation is x plus 1 whole square equals 2 into x minus 3. Expanding x plus 1 whole square, we can cancel out 2x from both sides of the equation. Arranging them on one side, we will get x square plus 7 equal to 0. It is of the form ax square plus bx plus c equal to 0, where the coefficient of x, that is b, is 0. So the given equation is a quadratic equation. The next one is x minus 3 into x plus 1 equals x into x plus 5. Multiplying throughout, we get x square plus x minus 6x minus 3 equals x square plus 5x. Cancelling the like terms x square on both sides and shifting all terms to one side, we get x minus 6x minus 5x minus 3 equal to 0, which is minus 10x minus 3 equal to 0. It is of the form ax square plus bx plus c equal to 0, as the coefficient of x square a equal to 0. But for a quadratic equation, a should not be equal to 0. So the given equation is not a quadratic equation. And the last equation is x cube minus 4x square minus x plus 1 equals x minus 2 whole cube. Expanding RHS, that is x minus 2 whole cube, we get x cube minus 8 minus 6x square plus 12x. So the equation becomes x cube minus 4x square minus x plus 1 equals x cube minus 8 minus 6x square plus 12x. Cancelling the like terms x cube, we get minus 4x square minus x plus 1 equals minus 8 minus 6x square plus 12x. Shifting all terms to LHS and simplifying them, we get 2x square minus 13x plus 9 equal to 0. It is of the form ax square plus bx plus c equal to 0. So the given equation is a quadratic equation. So here we notice that some equations like x minus 3 into x plus 1 equals x into x plus 5 may appear to be a quadratic equation but may not be a quadratic equation. And some equations like x cube minus 4x square minus x plus 1 equals x minus 2 whole cube may appear to be equations of higher degrees but can be a quadratic equation. So we can conclude that quadratic equations can be generated from several situations in the world around us and in different fields of mathematics. But before deciding whether an equation is quadratic or not, we need to simplify the given equation, then check whether it is of the standard form of a quadratic equation, that is ax square plus bx plus c equal to 0, where a not equal to 0, a, b and c are real numbers.